Hello everyone and welcome to Quesadilla Math with me, Mr. Padilla. Today we're going to be talking about transformations of functions graphically. In an ever-changing world, sometimes you need to learn how to transform, so let's get started. So function transformations is referring to taking the graph of a function and changing it in such a way that it moves the graph from one place to another. Really, it's creating kind of a new function, but we can think of it as actually transforming a function, as translating, stretching, compressing the graph of a function. To learn about this, we're going to be using and investigating how making changes in function notation can affect the graph of a function. To start off with, we're going to be using f of x as our original function. Really, it could be g of x, a of x, b of x, c of x, whatever we want, but for the basic form of it, we're going to be using f of x. Here's what we call transformation form. I know it looks like a big crazy equation with a lot of variables, but actually the only variable we have is x. Everything else here we call a parameter, and really when you're looking at an equation like this, those are not going to be variables or letters, they're going to be numbers. These are just holding the place of a value so we can talk about this certain type of transformation. So there are two main ways that you can transform the graph of a function. One of those is horizontally and the other is vertically. The parameters a, here seeing a times f of x, and d, here f of x plus d, are known as vertical transformations. And the parameters b, here multiplying x, and c, here being subtracted from x, are the horizontal transformations. Let's start off by talking about the vertical transformations and see how it works. So the first vertical transformation we're going to discuss is vertical translation, as seen here, represented by plus d on the outside of our original function f of x. So a translation you can also think of as a shift. Translation is a word from geometry that means to move an object without changing its shape or size, or without rotating it. So a translation is simply just moving an object around a space. And a vertical translation means that we're going to be moving up and down vertically. So as mentioned before, d is a parameter, which means you're not, when you see an equation like this in one of your, typically going to see a number instead of a plus d. Let's talk about what some of those types of numbers might be and the effect that they can have on the graph of a function. If d is a number that's greater than 0, which means positive number bigger than 0, f of x will be shifted up by whatever number d is. If d is 5, it'll shift up 5 units. If d is 10, it'll shift up 10 units, and so on. Now, if d is less than 0, which means if you have minus a number, or think of it as adding a negative number to f of x, that means you're going to be moving your graph down by that many units. Let's investigate what this looks like graphically. Okay, so now we're going to use the Desmos graphing calculator to take a look at the parameter d. The dashed line here in white will represent our original function f of x. This green one, or yellow highlighter color, will represent our transformed function. Okay, so as we change the value of d using this slider, it's going to change the graph in different ways. Let's try making d greater than 0. So right now d is equal to 0, and if d is equal to 0, obviously there's no change. That's what 0 means, right? But if we increase it, let's make d increase to about 2.8 here. Well, as you guys saw, the graph moved up by 2.8 units. If we increase it further to, let's say, 5 units, now you guys can see that every point on this graph, on our highlighter graph here, is 5 units above each point on our original f of x graph. So what if we looked at negative values for d? So this would be subtracting, so it'd be like f of x minus some number. Let's see what that would look like. As we make our value of d negative, you guys can see that it lowers it. The graph shifts downwards by the whatever the value of d is. In this case, I can move it all the way down to -10, and now every point on our highlighted graph is 10 units below each one of these points. And if I hit the little slider button, you guys can see how it changes as the value of D changes. So now let's take a look at our next vertical transformation. All right, so the next vertical transformation we're going to be describing is what's called a vertical dilation, or really what I mostly refer to it as is a vertical stretch and compression. So a stretch and compression or dilation really means we're changing the size of our figure, of our object. So if we look at our parallelogram here, a vertical stretch will mean that we are literally stretching our graph vertically like this, and a vertical compression means that we are squeezing our graph down flatter like this. So the parameter we're concerned with is a here. Now a is going to be a value that multiplies your function f of x. Alright, and what it's literally doing, since f of x is considered the range values of your function, right, the y values, you're literally multiplying all of the y values in the coordinates of your function, meaning that they're going to either stretch or compress the graph. When the value a is greater than 1, f of x is vertically stretched by that factor. So if a equals 2, for example, your graph is stretched 2 times as tall. When the value of a is a number between 0 and 1, so like a fraction or decimal that's smaller than 1 but still greater than 0, then f of x is vertically compressed by a factor of a. So for example, if a is equal to 1/2 and we have 1/2 times f of x, the graph will be vertically compressed by 1/2. Let's take a look at what this looks like graphically. Okay, so here once again, our dashed line is going to represent f of x, and this pink line will be representing our transformed function a times f of x. So right now a is equal to 1, and a lot like when you multiply any number by 1, when you multiply a function by the number 1, nothing changes about it. So it's still the same function. So now let's see what happens if we increase a and make it larger. Now I let a equals 2, and now you guys can see it has been vertically stretched, so that's now 2 times taller. You can think of it as taller, but really it's 2 times higher and lower at the same time. If I change it all the way to, let's say, 5, you can see it's starting to get really stretched out. And if we go all the way to 10, man, the graph is much more stretched out compared to its original version. So when a is a value greater than 1, the graph is vertically stretched by that factor. So now let's look at what happens with a number between 0 and 1. As we make a smaller value than 1, let's say here a is equal to 0.7, as you guys can see, it's as if we are squashing the graph from top and bottom closer to the x-axis, or at least closer to its center. And you guys can see as we get closer and closer to 0, the cool shape of our function is now starting to slowly become just a line. And if we make it a equal to 0, well, that's all we get. There is 0 height to the graph, if you can think of it that way. Values between 0 and 1 are what we call a vertical compression of the graph. Compression means to squeeze it down. Okay? You might be wondering, well, what happens if the value of a is negative? Well, that's a bit of a different transformation, so let's take a look at that specifically. When a is a negative value, or the way we describe it as less than 0, the graph is reflected vertically, and it does so across the x-axis. So a vertical reflection, you could think of as a flip, would look something like this. So let's take a look at how we can use a to make our functions flip. Coming back to our graph of f of x here, as you make a larger, the graph gets stretched, and as you make a smaller, the graph gets compressed. If you make it equal to 0, it flattens out to a complete line, And if you make it negative, well, it flips over. It is vertically reflected. So here I'm going to let a equal to -1. And when a is equal to -1, if you just see a negative in front of f of x, then really all you are looking at is just a simple, perfect reflection of your function. You could see that the y values completely change signs. So if this was a value here at -0 and -3, this one now has it at 0 and +3. So that's how the vertical reflection works. But I do want to remind you guys of something. The absolute value of a still works the same way as a positive number. So even when a is negative, it's still going to work the same as if a was positive. As I make a larger negative number, so if you're just thinking of the absolute value of a, then the graph gets stretched and reflected across the x-axis. As a is a negative number between -1 and 0, you see it is being compressed and flipped at the same time. So really, -a can be thought of as two transformations in one: stretching and compressing, as well as a vertical reflection across the x-axis. Now that we've talked about our vertical transformations, let's get familiar with the horizontal transformations. So the parameter c is what we call the horizontal translation, or the horizontal shift. The value of c determines how far left or how far right the original function is going to be transformed. Now, you're going to find the value for c either being added or subtracted from the value of x inside the parentheses of f of x. Now, the inside of the parentheses, I like to call the argument of the function. Inside the argument is where all of the horizontal changes to a function will occur. There's something to know about the argument of the function and transformations that happen inside there. They kind of work backwards from normal. As you can see here, we have x minus c. Minus a negative, you can really think of as being the opposite of a number. So, for example, the opposite of the number 5 is -5. Because of that idea, the values might be, are going to kind of be backwards from what you might think. Let me explain. So when c is greater than 0, f of x is going to shift towards the right. But because we have the minus c here, when c is positive, you will see f of x minus some number. Even though there is a subtraction there, since you're subtracting c is that positive value. Now, when c is less than 0 or a negative number, f of x is going to shift to the left, which makes total sense. Negative values are on the left side of the number line, and it does so by that many units. However, since you are subtracting a negative number, since we have our transformation here, x minus c, well, that becomes positive c. So when your value is negative, you will see inside f of x, in the argument, you will see x plus some number. So when you see x plus some number, that means you're going left. And when you see minus a number, that means you're moving right. So let's investigate how that looks in our Desmos graph. As we change the parameter c, we are going to see a horizontal shift in our graph by that many units. So let's take a look here. So I'm going to go ahead and move the slider to the right, making c a larger value. And it's nice because as I move the slider to the right, the graph also moves to the right. Just to give you a hint about what the equation might look in this situation, if c equals 7, then what you're going to be looking at is f of x minus 7. Even though it is a positive number, in the argument, it's going to have a minus attached, a negative attached. But it is a positive 7, so it moved 7 units to the right. Now, let's make c a negative number. Let's say about -3 here, and you can see that as you make a c negative, it moves to the left. So here at c is equal to -3, let's see what the equation might look like. You would get something like f of x minus -3. Now, you wouldn't normally see it written out like this, How you would normally see it is, since a negative times a negative is a positive, you would see this written out as f of x plus 3. So even though there's a plus sign in the argument for c, you should actually know that it's a negative value. Inside the argument, things kind of work the opposite. Once again, c is our horizontal translation, our horizontal shift left and right. When the value is positive, it moves to the right. When the value is negative, it will move to the left. However, you won't see it that way. So when you see minus a number, x minus a number moves to the right, x plus a number moves to the left. So now let's investigate our final transformation. So the parameter b, shown here being multiplying x, is what's known as a horizontal dilation, or a horizontal stretch and compression. So this works very similar to a vertical stretch and compression. Vertically stretching means that it is literally going to become wider like this, and a vertical compression works this way. It squeezes it horizontally. But because we're changing horizontally, once again inside the argument of a function, things work a little bit backwards. In this case, when b is greater than 1, f of x will be horizontally compressed. So a larger b value will actually squeeze the graph in like this, instead of stretching it like our vertical stretch and compression. Now, when b is a value between 0 and 1, this is when you're going to get the stretch happening. Values like 1/2 or 0.3 will stretch the graph horizontally this way. And just like with our a value, when b is less than 0 or a negative number, the graph is reflected horizontally across the y-axis this time. The same rules will apply, so let's take a look at how that looks graphically. Just like before, we are going to change the value of b to see how it affects the shape of our graph. So here we're looking at f of b times x. So b is literally multiplying the x values, which does some strange things to the graph. So as we make b larger, it's actually not going to make the graph larger. It actually shrinks the graph. It squeezes it in. We get this horizontal compression. So the larger b becomes, the closer it gets to the y-axis like this here. We are squeezing it in. Now, as we make b a value that's between 0 and 1, so like 0.9 here, 0.7, you can see it's getting stretched out horizontally, like it's being pulled apart like taffy. If we make b equal to 0, just like when a is equal to 0, it totally flattens out our function. But if we make b negative, you can see that we have what's called a horizontal reflection. It's reflecting across the y-axis. Now, as we make b a larger number in negatives, same again, we see a compression. If a is a negative number that's between -1 and 0, we get this stretch happening here. So now let's take a look at a few examples just to quickly see how function notation can be used to describe these transformations. In our first example, I'm giving you two different function transformations that look very similar. Here we have f of x plus 3, the function plus 3, or we have f of x plus 3. Slightly different intonation, or I like to usually say f of argument x plus 3. In our first example here, f of x plus 3, this is a d transformation. You can tell it's d because it's being added to the outside of f of x. All right, a multiplies the outside of f of x, c subtracts on the or adds on the inside of the argument, but d is being added to the outside of it. So that means it's going to be a vertical translation. And because d is equal to +3, we're moving 3 units up. The next part of the example we have here f of argument x plus 3. And even though you see a +3 inside the argument here, you need to remember that c is actually -3. Remember that in our transformation form, it's x minus that value of c. Since we have a plus here, that means that we must have a double negative. Negative times negative gives you this positive. Since c is -3, we have a horizontal translation 3 units to the left. So in these next couple of examples, we have examples of a being multiplied with f of x. If I have 1/2 times f of x, we say that's a vertical compression by a factor of 1/2. And if we have, in this case, a -3 times f of x, this is actually 2 separate transformations. One of those transformations is a vertical stretch by a factor of 3, since a is equal to 3. But since it's a negative, the negative on its own is its own transformation. This is a reflection across the x-axis. Sometimes function notation will show us more than one transformation at the same time, like the last example. Here I have f of x plus 4, then minus 8 on the outside here. The plus 4 tells me I have a horizontal translation, 4 units left, since again, my c value here would equal to -4. It's always the opposite of the value in there, of the sign. It's always the opposite sign that you see in the argument. And the -8 is a vertical translation 8 units down. Outside of the argument, it works just like you think it should. Subtraction means to lower, addition means to raise up. In our last example here, we have actually 3 different transformations. First of all, we have, because of this negative here, a reflection across the x-axis. So it's going to reflect vertically across the x-axis. We also have x minus 1 in the argument. Again, -1 means that actually our c value is positive, so we're moving, it's a horizontal shift 1 unit to the right. Notice how I wrote translation here, shift here, they mean the same thing. So I'm just trying to give you guys lots of vocabulary perspectives. Finally, we have this +3 here. That is going to be our vertical shift 3 units up. Since this one was -8 on the outside of our function, f of x was a shift down, +3 will be shift up by 3. So when you're looking at the function notation describing these transformations, know that you can have multiple transformations in one. Make sure you are make sure that you are aware whether they are horizontal or vertical transformations, and always look out for the signs. Very important. Thank you for joining me today, learning a little bit about transformations of functions. You know, if you can transform a function, you can transform your life. And I think that is a really hopeful statement in these trying times. So please, everybody, like and subscribe if you want to see further videos helping you through Algebra 2 this entire year. So please stay safe, wear your masks, and as always, I'll math you later.